Hi there, and welcome to this webinar on event-based motion in SolidWorks simulation. My name is Matthew, and what we're going to do today is have a quick look through the tools that are available to us in SolidWorks simulation to analyze motion in terms of an event-based situation as opposed to specifying a time-oriented system. We'll have a look a little bit at what that means shortly. First of all, what is our current approach to motion simulation? Well, at the time being, if we use the standard SolidWorks simulation tools, we have to specify a sequential movement of the system by specifying the exact time frames in which items occur. So we have to say action A will occur at 30 seconds and last for 3 seconds. Action B will occur at 25 seconds and last for so and so and so on and so forth. And we obviously, as I just said, have to know how long each of the items is going to occur for, and we need to specify adjustments to inputs or the structures of mechanisms by using keyframes. So we'll add a keyframe to the timeline and then make an adjustment just there. The downfall of this is that we have to work ahead of time and know exactly how everything is going to interact and when, which can take a lot of time and a lot of fiddling. There's a lot of time just adjusting the tiniest pieces to get them to behave as we want. So just as an example, if we have a look at the system I've got on the screen here, we've got just a box, a box which is being pushed around essentially all the way around into the tray at the other end. And setting this up, if we have a look at the actuator for arm 1, so that is this red one here, the very first actuator, you can see what I've had to do here is specify quite a long, complex function to define the movement of this particular actuator. And so we can see here the time graphs of each of the outputs. So we've got our displacement, velocity, acceleration, and just the jerk value in here. But we've had to work all that out in advance in order to get the system to behave as it is. Moving on to actuator 2 now. So this is the second arm just here. We can see I've had to work out an equally as long and complex function to give me a second output which is offset from the first. So we can see the outputs up here of all of the individual actuators here. I've had to work out those functions, the time frames, etc. in advance in order for the thing to synchronize as I wish. Now this is where event-based motion comes in. So first of all, what is event-based motion? Well, it's a lightweight version of a control system. So it's a very simple and easy to use tool for designers and engineers to control their systems, much like the software guys will eventually do. So we can create our motion simulations based on triggered events. So we can use either proximity sensors or previous events to trigger the next event. And we will see that a lot more in a second when we move on to the SolidWorks model. So finally, it is a tool for the designers and engineers to clearly and easily describe or explain their machine design goals to the controls team. So the guys that are actually going to be setting up the control systems. Sometimes trying to get across exactly what the designers and engineers are after can be quite a lengthy process. Here we can give animations or perhaps the actual event-based motion setup can be given to the controls team and they can take it from there. Just briefly, a sort of analogy that I like to use is the process of giving directions. So if you could imagine you stop someone on the street and ask for directions from place A to place B, and they say, well, drive forwards for 30 seconds and then turn right and drive forwards for another 45 seconds and then turn left and drive forward for 148 seconds, etc., etc. It's quite a long and convoluted set of instructions, and it's also quite unreliable. You don't know that they are saying the right amount of time to be driving for. Instead, what you want is a set of directions like we've got on the screen here just from Google Maps, and this is a process of triggered events. So once I reach a junction, so let's say have a look at step 3, take the first right turn. So once we get to the first junction, we're turning right. So these are all event-based actions, if you will. So once one thing happens, that triggers another event, and so on and so forth. And that is how we like to deal with things. That's most transparent to a human user. Okay, so key functionalities of event-based motion. Just before we jump into SolidWorks, we can simulate machine tasks and optimize cycle times. And as you'll see in a second, we can specify and change the parameters of our actuations very, very quickly and easily. It's a very easy interface to use, and we can set up our timescales and our triggered events very easily, and we can make edits very easily. Like I said before, we've got event-triggered controls. I'll bring those up as well. So we've got we can trigger events based on the start or end of other tasks. We can also input delays, and we can also use sensors, so a proximity sensor to detect when a certain component is within a certain distance in order to trigger another event or actuation. We've got servo motors, which are used to control the motions. So we can specify, instead of having a linear motion for 20 meters, instead we can have a servo motor, and then in the event-based motion we can specify how much to move this, the particular component and over what duration for that actuation to occur. And finally, we've got a very nice output or visual display, if you will, for the system based on a Gantt chart system, so we can see when each of the individual events is occurring and the duration on a timeline. So now let's jump over to SolidWorks and have a look. So what I've got here is just a little digger, and you'll see in a bit it is a little digger, but what we're going to do is just simulate the process of rotating around, scooping up some dirt, rotating back around, and dumping the dirt. So without further ado, let's go ahead and create a new motion study. Now the first thing we need to make sure that we do is add in our SolidWorks motion. So SolidWorks motion is up here. We've got SolidWorks motion available to us here, which is available in SolidWorks Premium, and that's the motion analysis tool. If I hit OK here, that gives us the opportunity to select motion analysis down here. Usually you will have animation and basic motion, but SolidWorks Premium gives us the opportunity to activate motion analysis. The other thing I will note while we are on the subject is the SolidWorks event-based motion. So this is the tool that we are having a look at now, is available only in the next package up from SolidWorks Premium. So in order to get access to event-based motion, you will need SolidWorks Simulation Professional. Okay, so continuing on now, I will just bring your attention to the mates. So hopefully most of you will be familiar with the standard motion tools that are available in SolidWorks, and the way in which SolidWorks Motion will pull through all of the mates that you've originally used to set up your study. So here I've got all of the mates that I've used to set up to constrain the assembly as it is at the moment. And you'll also notice that I've got 4 angular constraints in there, which are currently constraining the geometry to the exact position it's in. What we want to be able to do is change those orientations. So what I'm going to do here is just right click on those and suppress them. So now our system is going to be able to move within the study. Now it's worth noting that just because I've done that here, those are only local changes. So if I switch back to the model to my design interface and just rebuild those to get rid of the traffic lights, you'll see that those 4 mates are still active. And that's because those changes stay within the motion study. So you don't need to worry about making changes to the mates in the motion study having a big effect on your top level assembly. Those all stay within the study themselves. Okay, the next thing we need to do is go ahead and activate the event-based motion. So what we can do here is right click on the assembly. This is the first route to the event-based motion option, and you'll see here halfway down the list we've got event-based motion view just there. Or alternatively, we do have, and this is the quicker option, we've got a little icon over here at the right for event-based motion view just there. So if I click that, SolidWorks will switch me into the environment for the event-based motion. And you'll see it's very different. We can't see the timelines at the moment. Later on we will see our Gantt chart appear up here, and we can by all means switch back to our timeline just there, but in this environment we can add specific tasks as we go. We've also got a couple of options in here. Now these are the same options that you've got in the standard motion analysis tool, but we can change, for example, the frames per second. So this is how many frames are resolved. If you are saving it out to a movie or a video file, then that is the number of frames you will have per second in that animation video. We can also specify any contact resolution and the accuracy of the contact resolution here. So that's when we've got components coming into contact with one another. If we've got impacts or anything like that that we want to be able to resolve, for example, a ball bouncing off a surface is a very simple case, then we want to make sure that our contact resolution is up so that we can accurately resolve that collision. Okay, let's hit OK there. And the next thing for us to do is just go ahead and start adding our motors. So our motors button just up the top here allows us to come in and just pick off the geometry and specify motors. So the first thing I'm going to do is grab that outer cylindrical face. Let me just bring the digger back into the screen properly. And you'll see SolidWorks has defaulted to the rotary motor. So SolidWorks has recognized that I've selected a cylindrical face and is suggesting that I'm probably going to want a rotary motor in there, which is absolutely correct. Now I'm going to, in this case, grab my servo motor, and this is what allows me to then pick off and change values for the direction and displacement in the event-based motion tasks. So I'm going to grab a servo motor, and here we can specify whether that servo motor is controlled via displacement, velocity, or acceleration. In this case, I'm going to grab displacement and hit OK, and you'll see that we've got our rotary motor added in the tree just here. And I'm just going to take advantage of the capability to rename these things. So I'm going to rename this pivot motor, and you'll see the advantage of that later on. But this allows me to pick off what each of these motors is going to be called later on when I'm setting up the actual motions themselves. So next I'm going to grab a linear actuator. So let's just grab that ram arm there. And it's going to be a linear motion. Oh. Let's actually grab the right ram arm. There we go. And it's going to be a linear motion in the up-down direction. Now the thing we need to make sure we've kept an eye on is the way in which it's moving. So I've already specified that I want it to be linear, but the actual orientation of this component is going to change as we go on. So we want to specify almost like a reference coordinate system, and we can base that on another component. So in this case, in here we can select the component to move relative to, and I'm going to select that ram arm. So now the ram body. So now the ram arm is going to move in a linear up and down fashion with respect to that ram body, irrespective of the fact that the ram body might be changing orientation itself. Okay, now I'm going to grab that servo motor again and displacement, hit OK, and again this time I'm going to rename this guy. We'll call this the main actuator. And so now I'll just quickly whip through and apply the rest of my actuators. So I've got one on there, another linear motor with respect to that ram body, like so, and that's going to be my secondary motor. And finally, we've got one which is going to control the bucket on the end. So we will aptly name this guy the bucket motor. Like so. And that's all of our motors set up and ready to go. So now all we need to do is specify what we want each of those individual motors to do and when. So if I grab my event-based motion view, we can add a new task. So let's click in here to add the first task, and my task one is just going to be to rotate by 90 degrees. So this is going to be the first turn, I've put 0, the first turn, which is going to orient the scoop somewhere that we actually want it to dig up. Now for the time delay we don't want anything in there because this is going to start at the very instance that the motion study starts, and all we need to do now is select from my motors the pivot motor, specify that we want to change, so the action is to change the current value of the servo, not the server, and by a value of 90 degrees. In this case, we'll make it a long sweep over the course of 5 seconds. So now let's ask SolidWorks to calculate that and see what we get. like so. And that is it. That's the outcome of our initial setup. So next thing we will do is wind that back so we can scrub back to the beginning again in the motion study, and we'll add our next task. Now our next task is going to be to raise the main arm. So let's select to raise the main arm. And this time we're going to use the previous task as our trigger. So I'm going to select task 1 underneath the triggers, and we want this to happen at the same time. So it's going to turn and raise the arm at the same time. The time delay, we don't want to put a time delay on there for the time being. We're going to start at exactly the same time. And obviously in this case, for the main arm, we're going to select our main actuator. So we're going to change that, and this is where you'll see how small this guy is. So we're going to actuate by 1 inch, and we're going to do that over the course of 3 seconds. So let's ask SolidWorks to recalculate that and show us what we get. And so you'll see the digger arm raising as it turns, but because it's a duration of 3 seconds, it does finish raising before it finishes turning round. Let's add our task 3 now. So this is going to be to retract the secondary actuator. Can't spell today. We're going to base that on task 1 again. And again, we want that to be with the start. We're going to negate any delays. And in this case, we're going to grab our secondary actuator. Now, because of the orientation of this actuator, we're going to specify a negative 1 inch change. And I will show you why in a second. And we'll do that over the course of 2 seconds. So the reason we've got a negative value in here is all based on the reference coordinate system that we are using. So here you will see for my rotary actuator, or my rotary motor, sorry, we've got an anti-clockwise turning motion. My main actuator is in an upwards direction, so positive is in the direction of that arrow. My secondary is acting in the forwards direction, and my bucket motor is acting in the backwards direction. So in this case, actually, I've probably stuck that in the wrong, and that needs to be a 1 inch. So if we run that now, no, I was right the first time. So we want that to retract. I've spec'd it wrong. So there we go. So the arm is going to lift up and extend out as we go. So the actuator is pulling inwards, because that direction of the secondary motor is in that orientation. So next, our task 4, we're going to finally open the bucket. So this will be the last one before I whip through and add all the tasks at once. So we're going to open the bucket, base that on the first task again. In this case, we're going to use start again, but we're going to put a delay on there. So we're going to put a 0.5 second delay on there, just so that it's not starting exactly the same time as all the others. And we're going to grab that actuator for the bucket, change it by 1 inch over the course of 1 second, and we'll ask SolidWorks to animate that. We'll see what we get. So you see the arm coming up and the scoop extending this time, so we're ready to drop down and actually scoop in. So now let's go ahead and add all of the tasks that I'm intending. So after we've opened the bucket, we're going to lower the main arm. That's in preparation for the scoop. In order to start the scoop, we're going to retract the secondary. Then we're going to extend the secondary. Now these are all things that are going to happen at the same time. So our extension of the secondary, our raising of the main arm, and our closing of the bucket are all going to happen at the same time. So it's going to lift and scoop at the same time, which is what you normally see them doing. So we're going to then pivot back, and we'll probably go back about 180 degrees, so all the way over to the other side to dump the dirt, and then finally we will dump the dirt. So next we need to set up the tasks. So these are our triggers. So what's going to kick off each of these individual tasks. So first one I'm going to base on task 1. Next one we will do the same. So we can all base those off that first task. But then extending the secondary is going to be the next phase, if you will, of the process. So after that, I'm going to base these on task 6. So that's after we've retracted the secondary. We're going to extend it. We're going to raise the main arm. And we're going to close the bucket. Then finally, we'll pivot back. So after we've finished raising the main arm, we'll pivot back. And once we've rotated back round, so after we've pivoted back, we will dump the dirt. So I'm going to whip through here and just stick in a couple of delays on here. Now these delays aren't exactly necessary, but you'll see that it's quite nice sometimes to have a small delay in there just for aesthetics, so it looks a lot better instead of having everything going immediately one after the other. So a very small delay just makes the whole thing look a lot smoother. And now, so here, this is where we get real benefit from naming our motors and giving a description for each of our individual tasks. Because now I can whip through, so for lowering the main arm, obviously I'm going to grab my main actuator. For retracting the secondary actuator. Again, secondary. Raising the main arm is going to be a main actuation again. Closing the bucket is going to be using the bucket motor. Pivoting back is going to be the pivot motor. And then finally, again, we need to access the bucket. Now, all of these are going to be changes, so I'll just whip through and make all of those changes now. Like so. And now let's go through and specify what values we're going to have in here. So we're going to bring that back by 1.5. And that's going to be a 0.5 actuation, so it's a very small retraction, followed by the extension, which is going to be a lot larger. Raising the main arm just a 1 inch, we'll come back 1.15 on the bucket, we'll spin back by 180 degrees, and then we'll flip the bucket by 2, so we're going to open that bucket right out in order to dump all of the dirt that's in there. So finally we just need to stick in all of the durations for each of these events, which is very simple. You'll know how long each of these things is going to take. So the nice thing is we just need to specify when it starts and how long it takes, and SolidWorks works out the rest. So like so. And then finally all we need to do is click calculate, and SolidWorks will whip through and hopefully give us the result that we're after. Now you'll notice that that has stopped there, and it's worth bringing this to your attention now. SolidWorks will still be based upon the original motion study, so we've got our keyframe set to 5 seconds for the time being. So I'm going to drag that out to 17, and that's going to allow the study to be 17 seconds. So switching back to the event-based motion now, hopefully we will see a big difference in that it will run all the way through to the end. So now we've reached that end phase there. Scoop's going to drop down, and then we're going to scoop up that dirt, bring it back up, rotate round, and drop off the dirt at the end. Okay, and it really is as simple as that. It's a case of picking out each of the individual tasks that you want to, 1, produce, and 2, how you want to trigger each of those. And then we can specify how much of the changes we want to use and the duration of each of those changes. Now, before we do go, I will just show you another example I've got, just because we haven't seen the proximity sensors yet. So let me grab this sorting device up, and we'll hit play here. And you'll see what's happening is the device is sorting each of the individual block types into different bays. Now we can do this by using proximity sensors, and we've got access to the proximity sensors just in our standard CAD interface. So up here, you've probably seen it before, never used it. We've got a sensors folder, and if I right click on there and add a new sensor, we can come through by selecting our sensor type as a proximity and specify our own sensor. So in this case, for my sensor location, I'm going to grab, let's say, this face here, and you see we get a nice red line signifying the sensing direction, if you will. Now we can change the direction of that, so we've got in here our proximity sensor direction, so we can grab other edges, other faces to change the orientation of that line if it's not normal to the surface. And then we can specify which components we are detecting. So in here, if I hover there, we've got components to track. So this particular sensor, we've got two here, you see, was set up to track the two solid blocks. So we just select those, and now that sensor will be seen to be on when those two red blocks fall within the sensing range. We can change that sensing range finally by coming in here. So if I change that to, let's call it 10 millimeters, you'll see that that line drops right down, and so now the sensor will only be active if either of those blocks is within that tiny range just there. So we'll see, if I check my sensor 1, we've got that one face there, we've got a 12mm sensing range, so we've got the tiniest of ranges just peeking out above the material thickness here for when the red blocks are actually sat on that surface, and then you can see we've got the two red blocks selected in there. Likewise for sensor 2, we've instead selected the hollow blocks and activated the other face, so the sensor 2 face just there. Okay, and that really is all there is to it. So here, what we've done is specified one particular action for when sensor 1 is activated, and an alternate action for when sensor 2 is activated. So here we've got sensor 1 when it is on, so under my alert conditions, when sensor 1 is on, we've got the actuator 1 changing by 75mm, and that's over the course of a second. Then we've got retraction of that actuator immediately afterwards. We've also got at the same time a push of the solid block into bay 1, followed by a push of the hollow block into bay, retraction of that actuator. Then we've got the push of the hollow block associated with sensor 2. So we just run that again once more, and you can see what happens as each of these are activated. Okay, and that really is all there is to it. I do urge you to have a go yourself with event-based motion if you have it available to you. It's a really handy tool, and there's always things you'll discover that you can do that you didn't realize were available to you before, and there's probably a number of things that I haven't shown you yet on here that perhaps might come up again soon, but for the time being, I do urge you to have a go yourself. So, thank you for joining me, and do tune in again for our future upcoming webinars. We've got assembly validation tools in SolidWorks coming up next week with Dave. We've also got design tables to drive designs in SolidWorks, and the first of a couple of webinars we've got coming up on piping in the SolidWorks routing functionality. So thanks again for attending, and if you do want to get in touch, you can do so by the contact details you've got on the screen there. You've got our website, our phone, and our email address just there.